Hello and welcome to this brief presentation. We are glad to present to you our graduation project sponsored by Siemens. In this demonstration, we will start by showing you the project components, then we will talk about the problem we want to tackle and our proposed solution to this problem. Then we will talk about the architecture of our project and its details, and we will go through each component including the V2X, cloud, diagnostics, firewall, log and trace, update and configuration and cryptography. Finally, we will show you the ADAS use cases of the project. This is our project components in details. According to the National Highway Traffic Safety Administration, there were about 5 million police-reported car accidents for the year 2020. One of the largest factors that contributes to how large this number is the fact that a driver has limited awareness of his surrounding environment. We now present to you our own solution that integrates ADAS with vehicle-to-everything technology to provide not only safety but also a better and more comfortable driving experience on the road. And by exploiting the adaptive AUTOSAR platform, V2X hasn't been more faster. The architecture consists of two ECUs each on the same vehicle. The Ego vehicle contains a NVIDIA Jetson Nano which hosts the AI models that is connected to a Logitech camera. A Raspberry Pi 4 Model B which is connected to a GPS module which is necessary to fill the V2X messages with the current location of the vehicle. The Pi hosts the adaptive platform with the newly added V2X functional cluster. Both the Pi and Nano communicate through SPI to exchange action codes. The ESP32 acts as bridge between the two ECUs. Each action code represents an action that should be taken by the Pi. For example, the Nano might detect a red traffic light and hence send the appropriate action code to the Pi to take. Now we showcase the internal implementation of our adaptive AUTOSAR instance and the clusters we implemented. We start with the execution management is one of the main clusters in the adaptive platform. It is the first cluster to launch after the OS and is responsible for launching all other clusters and the adaptive applications. The communication management is responsible for all the communication between adaptive applications. It implements a service-oriented architecture which applications use to communicate. The state management is project-specific and is responsible for all aspects of the operational state of the adaptive AUTOSAR platform, including handling of incoming events, prioritization of these events, requests to set the corresponding internal states. The identity and access management provides a framework for access and control for requests from adaptive application on service interfaces. The log and trace functional cluster is responsible for managing and instrumenting the logging features of the adaptive AUTOSAR platform. The logging and tracing features can be used by the platform during development as well as in and after production. The cryptography cluster is an API for common cryptographic operations and secure key management. The update and configuration management is responsible for installing, updating and removing software on the platform. The firewall cluster manages and configures the host-based firewall on the ECU where the adaptive platform is deployed on. Additionally, the firewall offers interfaces to adapt the firewall rule configuration according to the vehicle state during runtime. The diagnostics cluster plays a pivotal role within the adaptive AUTOSAR architecture by overseeing the health, monitoring, and management of various vehicle systems. This cluster is responsible for implementing a comprehensive diagnostic strategy that enables real-time detection, reporting, and resolution of faults. For this project, we introduced the V2X stack into the adaptive AUTOSAR as new cluster. Furthermore, the app layer components like the VDP and LDM are implemented as adaptive applications. Now we go in details with the V2X. The V2X cluster consists logically of layers. 3 stacked layers which are the facilities, basic transport and geo-networking. and 2 vertical layers, which are the management and security. The facilities layer is responsible for common message management for data exchange between vehicles, providing periodic CAM messages and DENIM messages according to certain situations. The basic transport layer implements the BTP protocol and provides services to both the facilities and geo-networking layers. The geo-networking layer provides a set of network layer functionalities that enables ad hoc communication and supports distribution of messages among the vehicles. The management layer manages the operation of the V2X stack through a number of services and provides some interfaces for the adaptive applications above, like the VDP. Later on, at the end of the demo, we will show how the project works through 3 different use cases, which are the lane detection, collision avoidance, and traffic light detection. Now onto the second use case, where both vehicles communicate with the cloud server hosted by DigitalOcean using VISS protocol. The next demo showcases that communication. As we can see, we are connected to the cloud server using remote SSH connection. The cloud server implements the VISS client on the Raspberry Pi, which represents the main ECU on the vehicle. We can see the AeroCom service registry, as well as both fuel warning app and gateway, which implements the VISS server. The GUI runs on a separate PC and shows the signals received by the cloud. Now we run the VISS client on the server side. Then we launch the applications on the Pi side. Now we can see the signals sent by the vehicle to the cloud changing on the GUI. When the vehicle enters a zone with no nearby gas stations, the GUI shows a pop-up warning. The Diagnostic Studio tool is a versatile and user-friendly solution designed for the adaptive AUTOSAR diagnostics server, offering a comprehensive suite of diagnostic services. With this tool, users can effortlessly perform essential tasks such as reading and writing data by ID, transitioning between different sessions, e.g., from programming to default, adjusting security levels, and sending test or present signals, both manually and automatically. What truly distinguishes Diagnostic Studio is its commitment to user-friendliness and aesthetics. The tool offers an elegant and user-friendly interface, ensuring an enjoyable and frustration-free experience. Whether you are an experienced diagnostics expert or just beginning your journey, the clear and intuitively designed navigation system will facilitate your tasks with precision and ease. Our core values revolve around ensuring the highest standards of data integrity and consistency. The tool employs rigorous consistency checks during input, guaranteeing pristine data quality. At the same time, we prioritize user comfort and satisfaction, offering a diagnostics-oriented user interface that streamlines your experience and accelerates your diagnostics processes. Diagnostic Studio is not just a one-size-fits-all solution. It's fully customizable to adapt to your specific needs. Tailor the software to your unique requirements, ensuring that it aligns perfectly with your workflows and objectives. Furthermore, our commitment to future-proofing is evident in the tool's extendable architecture, designed to accommodate emerging diagnostic needs and technologies. Now we demonstrate how the diagnostics tool works. Upon initiating the server on the ECU, our initial step is to navigate to the Home tab, where we configure the connection settings. These settings encompass specifying the device type and selecting the appropriate connection method. Following this setup, we proceed by clicking the Connect button. We seamlessly transition to the Diagnostics tab, where we embark on executing diagnostic services on the ECU. Our journey commences with the RID Data by Identifier service. As we engage with this service, we can promptly observe the ensuing changes on the diagnostic console. This console provides a comprehensive display of service information, including critical details such as source and target addresses, the required service, and the ultimate service outcome. Next, we move on as we want to apply the right data by identifier, but the service is not performed as the diagnostic states that you are trying to perform the service in the wrong session. so perform the session control service by changing from default session to programming session. As we switch to programming session, the tool starts sending the tester present message automatically at periodic intervals. We use the service settings to stop printing the automatic messages of the tester present on the diagnostics console. Now we will try to write once more, which, as shown by the console, didn't work as it is not supported for this security level. So, we begin to perform security access service by changing to a higher security level, which is the programming security level. We will use the pseudo-random number generator in order to be able to verify the security level. If we use a pseudo-random number generator not the same as the one compiled with the server code, it will give a security access denied error. Now, we use the same one compiled with the server code and we get the security access granted. Only on this case we can apply the right data by identifier service. In the final leg of our journey, we perform a validation check to confirm if the data has indeed been successfully written to the server. Now we will walk you through the different software tools implemented in this project that serves multiple clusters. We start with the firewall cluster.
The process of the firewall cluster begins when it receives the filtering rules from the machine manifest, then it proceeds to set up the underlying firewall in the kernel, particularly the NFQ provided by the IP tables. When a packet is sent, it's forwarded to this NFQ where it's compared against the filtering rules. If they match, the packet redirected to the receiver; if not, it's dropped. The following demo shows the firewall process. We have the firewall GUI which tracks the TCP connections in the system and packets inspection outcome. Now we simulate a SYN flood attack by sending a great number of packets to port 5555. Notice the red lines in the GUI which confirms these packets are dropped and the system is working normally.
Now moving into the log and trace cluster. Log and trace tool is a GUI tool that supports filtering and searching in log messages from different perspectives. As a GUI tool, log and trace.jar can be run from both Windows operating system and other Unix-based OS, including Ubuntu. The application has a simple and fast response interface and is capable of searching and filter the log messages using either search keywords, starting and ending date. We can also filter log messages using log level like error and warning. You can see its functionalities through this demonstration. Now on to the update and configuration demonstration where we will install a software in the vehicle which turns the LED on. On installing the software, the LED will turn blue, and on update the LED turns green and it turns off when we remove the software. First, the user requests software package update from the cloud and the request is accepted. The user connects to the vehicle through Bluetooth using the Blue Dot mobile app. When they are connected, the software package is downloaded to the vehicle as we see on the bottom left folder. Then the UCM parse and install the package successfully into the PI and the LED turns blue. The user receives another update from the cloud and follows the same steps to update the software on the vehicle, and we see the LED turns green. Next, the user receives an update from the cloud to remove the software and proceeds to uninstall it. We notice the LED turns off when the update is completed. The main importance of the UCM is the over-the-air update, which serves the dynamicity of the adaptive platform during runtime, which we showed throughout this demonstration. Now we are going to explore the cryptography cluster. The FC Crypto offers applications and other adaptive AUTOSAR functional clusters a standardized interface, which provides operations for cryptographic and related calculations. These operations include cryptographic operations, key management, and certificate handling. FC Crypto manages the actual implementations of all operations, the configuration, and the brokering of operations from applications to implementations. The standardized interface is exposed by the Crypto API. The FC Crypto and its Crypto API supports both public key and symmetric key cryptography. It allows applications to use mechanisms such as authentication, encryption, and decryption for automotive services. FC Crypto are grouped into different providers. Each of them implements specific domain of cryptography-related functionality, which are the crypto provider, key storage provider, and X.509 certificate management provider. Now into the details of the crypto providers. First, the key storage provider. It is responsible for secure, confidential, and authentic storage of different type key materials, whether public, private keys or seeds, and other security-critical cryptographic objects. For example, digital signatures, hash, MAC or HMAC tags. Second, the crypto provider is responsible for implementation of all supported cryptographic primitives. It supports multiple instances of the crypto providers. Each instance of crypto provider represents single holistic software or hardware-based implementation of some set of cryptographic algorithms. Third, the X.509 certificate management provider. It is responsible for X.509 certificates parsing, verification, authentic storage, and local searching by different attributes. Also, it is responsible for storage, management, and processing of certificate revocation lists (CRL) and delta CRL. It supports of requests preparation and responses parsing for online certificate status protocol. It supports only single instance of the CMP, and it is completely independent from crypto provider and key storage provider implementation. For our implementation of the cluster, we use the Crypto++ library. Crypto++ is a free and open-source cryptographic library written in C++. It provides a comprehensive set of cryptographic algorithms and features, making it suitable for a wide range of security applications. Here are some key features and information about Crypto++. Cryptographic algorithms. Crypto++ offers a vast collection of cryptographic algorithms, including symmetric ciphers like AES and DES, hash functions like SHA-1 and SHA-256, message authentication codes like HMAC, public key cryptography like RSA, DSA, and ECDSA, key exchange protocols like Diffie-Hellman, and more. Cross-platform. Crypto++ is designed to be highly portable and supports various platforms, including Windows, macOS, Linux, and Unix-like systems. Performance. The library focuses on providing high-performance implementations of cryptographic algorithms. It utilizes CPU-specific instruction sets, such as SSE2, SSE4, AVX, to leverage hardware acceleration when available, resulting in improved performance. The library supports other features like extensibility and standard compliance. One major design decision of FC Crypto is to separate to the extent possible the three domains dealing with cryptography, key management and certificate management. To simplify interaction between domains and abstract interfaces from the actual object, the I/O interface has been introduced as an intermediate layer between the persistent resource and the runtime object. The I/O interface enables the user to deal with the stored key without knowing how it is stored, read, or written. It abstracts the access to the key material as well. Behind the scenes, the I/O interface can point to one of two types of storages: volatile memory and persistent memory. In this project, our implementation of the FC Crypto supports the following contexts: symmetric block cipher context, encryptor public context, decryptor private context, message authenticated code context, authenticated encryption context, random generator context, hash function context, signer private context, verifier public context, sign and code private context, and message recovery public context. And now we present the ADAS use cases, and we start with the first use case: lane detection and keeping. As shown in the video, the goal is to allow the vehicle to detect the lane lines and be able to keep moving in between the lines. The algorithm works by detecting the two lane lines given the camera frame and outputting the steering angle needed to stay in lane. If the vehicle detected only one lane line, the left line for example, this means that the vehicle needs to steer right, and this is exactly what the algorithm does. Having known how the algorithm works, we can now watch the different views of the algorithm in action. The second use case is collision avoidance using V2X. This works by periodically sending CAM messages between the two vehicles. Whenever a danger zone is entered, a stop action code is sent from the Nano to the Pi to stop the trailing car. The third use case is traffic light detection. This is done through two different stages. Firstly, detecting the traffic light, then classifying whether it's red or green. As shown in the video, the car stops when the red light is shown and moves when the green light is on. Special thanks to engineer Mona Helmi, the owner of the project idea and its initiation, and our first supervisor, for her great management, encouragement, responsibility, invaluable advice and continuous guidance. We would like to show our special gratitude and thanks to Dr. Mohammed Taher and our sponsors, Siemens represented by engineer Mona Helmi and engineer Ahmed El Fashawi, for providing us with every tool and equipment we needed and showing us great support. Moreover, we would like to thank them for their great help and their continuous availability. Finally, we would like to thank every team member for their great contribution and congratulate them for the success of this project. Thank you very much for watching.